Welcome to part 3 of this Getting Started guide in Flux. We'll be doing the fun part of laying out the PCB today. PCB layout requires knowledge of the non-idealities that physical features add to your schematic, and it also requires an artistic touch, which is why it's many people's favorite part of electronics. If you need to get caught up on schematic and project setup, see the previous 2 videos in this series. To provide some project context, we're going to be removing this potentiometer and replacing it with a digital potentiometer for the buck converter. We're also going to be replacing this switch with an ESP32, which will control both the buck converter and the digital potentiometer. That way we don't have to turn on and off the board manually, and we can turn it on and off based on Wi-Fi triggered events. For example, when a meeting starts or when your phone goes into Do Not Disturb mode. All right, let's get started. We're going to pick up right where we left off in the schematic tab. And to get started laying out your PCB, hover over here and click on the PCB tab. Here, as you can see, we have parts everywhere. One of the first things I'm going to show you how to do is remove these designators and values from your components. As you can see, when I'm laying it around, the bounding box around it highlights these values as well. Under the Rules tab on your left panel, I'm going to activate these rules that I've created, and as you can see, the designators just disappeared. To quickly explain how this is working, I have a selector which selects every object that has the name reference, and I'm setting its value to false. Or the enabled property, I'm setting it to false, and using an important flag to override it. If I could turn this off, I can also set the font size. As you can see, I'm going to turn that off and the font increases. This is a really powerful tool, so feel free to look in the Flux documentation for more information about it. I'm going to set it to false when we're laying out the board, but when I get back to positioning the references, I'm going to turn this back to true. The other rule I'm going to add is the same thing. I just select any component, any object with the name value and set its enabled value to false. As you can see now when we're moving around parts, the bounding box only circles the remaining silk objects. Another thing to note is that rule sets are copy pastable across Flux. So if you have my project open, you can right click, copy, and paste in your project. Additionally, you can set these rule sets into a template as we talked about in the first video. The first step to PCB layout is part placement. I just realized we haven't even done the layout for our submodule, so let's start with that and then come back to the parent project. Now we're in the buck converter module. Let's start laying this out by going to the PCB tab. So to drag parts, you can just click on them and drag them. You can also select them from the object tree if they're hard to reach. Let's say I want to grab C3. I can go into the object tree to select it, or I can just select parts like so. Right now, I'm just moving the parts out of the way to make it easy to drag them in. Before we start laying out this design, I want it to be on the bottom layer. So I'm going to select all the components and press F. Doing this reverts everything to the bottom layer. As you might have noticed, it looks like the pins have flipped, but that's because we're still looking at the board from the top view. So to flip the viewport, just click on this button at the top right, and now we're laying out the board from the bottom. I need to take this time to backtrack to 2 videos ago when I told you how to create modules. The first thing I did was drag in this terminal, and that's a mistake. If you're seeing on your PCB that you don't have a black background and you cannot see air wires to your components, this means Flux thinks you're creating a part and not a module. How you create a part and not module is you start by dragging in a terminal. If you drag in any other object, like a ground or one of these components, Flux will create a layout object for you. So let me show you how to properly create a module. You drag in your first part, and then you say, oh, let's connect it with a terminal. Because you've dragged in this part first, you'll see the nesting in Flux is that you have a layout object and then all your components. So that's the correct way to do it. What we did was we dragged in the terminals first, which is why you don't see a layout object and everything is nested under footprints. So let me show you how to quickly fix this. We're going to cut our project, then go to the PCB view, delete the footprint, which is an artifact of the layout. And right now you can drag in a part like I just showed you, or you could add a layout. And when we paste our parts back in, as you can see in the PCB view, everything is nested under components. So now we can go back to laying out our board. If you perform the fix, you probably also have to rename your terminals as well as your components. Now let's go back to PCB to start laying out the module. As you can see, now we have air wires on the parts and we can get started. I typically look back and forth between the schematic and the PCB to know what part I want to place where. For example, C1, C2, and C3, I want to place near the VDD pins. So I'm going to grab C1 and move that here. You can press bracket keys to rotate your parts. And let's grab C2 and C3. When laying out buck converters and general ICs, you want to place the decoupling capacitors close to the power supply pins. That way you can minimize the parasitic inductance because these inductances counteract the attenuation effect of your capacitors at higher frequencies. Because of this, you also want to place your lower value capacitors closer to the VDD pins. To check the values of the pins, you can either remember from the designators or you can click on them and look at the panel on the right. I can see C3 is a 0.1 microfarad and C1 and 2 are 10 microfarad capacitors. And about spacing, you want to keep things dense, but if you're unsure about collisions, you can always go into the 3D editor to get an idea of what's going to collide. I'm going to lay out the rest of this board. So you might have noticed that when you add a terminal, it spawns an object on the PCB, and this kind of acts as a test point so you can probe it later on. Right now, if you want to remove it, you can add a property that says exclude from PCB. If you set this value to true, as you can see, VN disappeared. I'm going to set it back to false so I can keep these terminals as test points. And I'm going to shrink their size really quickly. So I'm going to set them all to 0.4 millimeters or 0.5 to half the size. Place that nearby, and I'm going to do the same for the rest. This board can be routed pretty simply, so to start routing, all you have to do is click on a routing touch point and you will see a trace come up. This is very similar to routing in schematic. If you press F, you can change the elbow direction, and if you press W, you can cycle through sizes of traces. Now I'm going to quickly lay out this module, and I'll show you some more advanced layout techniques when we get to the parent project. And now that we're done with all our changes, don't forget to publish them with CTRL P and publish. After publishing our changes, we should find them reflected in the parent project. Now I'm going to move everything out of the way so we can start aligning these on-air letter modules. Okay, let's first get everything set up so we can spell out the word on air. And now let me show you how to align these to the tops of each other. If you right click, click align and press on align tops, then all these letters will be aligned like so. And if you want to space them evenly, you can right click, press space evenly, and space evenly horizontally. Now if I want to move these letters to the right, I can just shift and move it in one direction or the other. I only want to move it to the right, and I will do the same here. I'm noticing that the spacing's a little off, so feel free to change things up. And let's move these letters to the right and the left respectively. Right now it looks like these letters are ever so slightly above the x-axis of the board. So let me show you what I think is the most effective way to fix that. If you click on a letter, we can add an object-specific rule, which is a layout rule, and let's call it position Y. This overrides the position rule just in the Y direction, so say 0. Now, the letter N will be set to 0, but how do we get that across to the rest of them? You can right-click, press Copy Special, and copy layout rules, and click on each letter and paste with Control V. You can do the same. You can select the modules using the object tree or in the canvas. And now all our components are centered using this position Y rule. Now we're ready to adjust the board size. So to do so, you click on the layout node, either in the object tree or in the canvas by clicking on the word layout. And as you can see, a bar came up here where you can edit the size. Let's say I want to shrink it in the X direction to 140 millimeters by, let's try 100. Okay, that looks pretty good. And we can realign our letters. In this case, I'm going to adjust the board size before laying out the rest of the components because my letters are the main bottleneck here. We can add a corner radius, like 3. We can also change the shape to a circular board or a rectangular board, but I'm gonna stick with rectangular board. It looks like we can shrink the sign down a little bit. It's a little bit tall for my taste. If you look closely, when we added these roles to the toolbar, all it did was auto-populate these roles in the object-specific roles. So there are more roles you can use to modify the board, such as the stack-up role. And we're going to use that to change the stack-up from a 2-layer board to a 4-layer board. And down the road, you're going to be able to customize your own stack-ups. With that, component placement should be pretty straightforward. I'm going to bring all my components back onto the board and press F to flip them to the bottom, except for the USB connector. Now that I'm happy with my part placement, I'm ready to start routing. Just like before, to start routing, you click on these routing touch points and you can click around to set your trace. You can press W to cycle through the trace widths and F to change the elbow direction of your trace. Now I don't like the default trace widths these come with, so I'm going to show you how to change that. There's a preferred trace widths rule in Flux that allows you to change which trace widths these snap to, and it only applies to net containers, meaning you could apply it to all your nets or specific nets that you want. For example, I'm going to set a default one to all my nets. Preferred trace widths. And the default is 150 micrometers, 300 micrometers, and 500 micrometers. I'm going to go with 7 mil, 10 mil, and 20 mil just as a default. And I know specifically for this net that I need a minimum of 20 mils to handle 1 amp of current. I'm going to place a trace down to find the net, because when you click on the trace, it'll show which net container it is. And I will add another object-specific rule, which is preferred trace widths. And just to cycle through the trace widths I want, 18 mil is actually my minimum. I'll do 22 mil for preferred and then 24 mil for maximum. And to get this information, you can use a PCB trace width calculator. There's a lot of factors that come into play: how much temperature rise you're willing to tolerate, what's the resistance you're willing to tolerate, the voltage drop, power loss, as well as if your layer is internal or external. So once you have those numbers, you're ready to start routing. So here I'm on the bottom layer and I want to connect the anodes together. I'm going to press W to get to my maximum trace width. Another way to edit your trace widths is to hover onto the trace segment and you can modify it like this. This adds a trace width property which will take precedent over any parent rules. And to show you how to use parent rules, let's add a rule set to change the trace width for all the traces in a specific net. So to select a net container, you use the hashtag operator, and let's go look for a net. Let's say we want to change the trace width for this net. Let's rename it to net 27. When we go back to our rules, we can select net 27, which selects the net container, and we can add a trace width rule. Now we can change a trace width to whatever we want. Because these traces have object-specific rules, they take precedent over this rule, but if you use the important flag, as you can see, we just changed the trace width to 10 mils. So this is a powerful way to change trace widths and properties of objects after the fact. I'm going to turn this off because I do want them to be 24 mils. I'm going to finish routing the rest of the board. As a general tip for routing, I would route your high frequency signals first and then move on to power. That's because the tracks you lay down first will have direct paths, whereas the tracks you lay down later will need to snake around using vias. You want to make sure your most important signals have the cleanest path and the least amount of parasitics. Vias and long trace lengths add to those parasitics. The high-speed signals on this board would be the USB data lines. So let's start routing those first. To begin routing an impedance match differential pair signal, you just begin routing like you would any other trace. If you want to route a single trace, all you have to do is press Command or Control to cycle between impedance diff pairs or a single trace. As of right now, Flux doesn't technically support via popping, but let me show you a trick to work around it. If you place a trace segment here and right-click to switch layers and place another trace segment and finish your connection, then because we've placed two trace segments here, we can just drag the vias apart from each other, like so. And we could do so vertically. Now, if you're curious about the calculated values for this impedance controlled pair, you can go into the net container and look at the properties which got us to these calculations. You can cycle between the actual and computed tabs to get an idea of those figures. In order to set up an impedance control trace, you have to configure it in your part. So in this part, if you hover over the pins, you can see that it has a target controlled impedance of 90 ohms with a 15% tolerance. The other piece of the equation is the stack-up you use. So Flux is computing the impedance of this pair according to the stack-up as well as the target impedance you've set on your pin. This means if you change your stack-up, your traces will have different parameters to meet the target impedance. As of right now, these are the supported stack-ups in Flux, but very soon you'll be able to configure your own according to your manufacturer. So far, we've been routing with the Copper Fills visibility disabled. If you want to toggle their visibility, you can click on this button next to the layer. I like to route without them on because it makes it easier to see the traces and the components. If you want to disable Copper Fills per layer, you can go into your object tree and under nets, you can find all the ground fills that you might have. Here I have two. To disable it, let's add an object specific rule, which is connected layers. And here you can toggle which layers that you want them to be connected to. So let's add the same thing here. Let's say we only want it to be connected on the top. Because I've only selected the top layer as the connected layer, as you can see, we have a top layer here. But if I toggle the visibility of all my other layers, they do not show up. When toggling the copper fill, you might have noticed that there are these stitching vias. To adjust the stitching vias, you can go into the nets container, find the ground container, and add an object-specific rule relating to the fill stitching vias. You can adjust the fill stitching density to change how far the vias are placed from each other, and you can also set it to 0 to disable stitching vias. Additionally, you could change how far the fill stitching vias are offset from the board. I'm going to be removing the fill stitching density to preserve the look of the board. If you're working with ESP32 or any other RF product, you'll know that you can't keep copper underneath its antenna. How I've gone ahead to remove this part of the fill is to add a small keep out pad object by going to Components, Add, and Pad, and I give it these object-specific rules. The keep out adjusts how far the keep out is applied, and I set the hole size to 0, so if I want to place it on the board, it has a minimal impact on my design. You also want to set the connected layers to all and set the pad type to standard so that the keep out applies to the copper in all your layers. Now I'm ready to start laying out the board, so I'm going to toggle off the top layers for ease of routing. As I was looking through the board in 3D view, I realized there's no way for me to mount it to the 3D printed chassis. So let's add mounting holes to the design. I'm going to go back to the schematic to make sure they have a nice place and just search for mounting holes. And now we're ready to place them on the PCB. Let's switch to the top side. I'm going to modify the positions to give them a nice even number. And now when we switch back to the 3D view, you can see we have mounting holes for our board. Before you order the board, you want to check for any DRCs in our problems panel. So over here, we have a bunch of component overrides. I usually ignore this, as well as boards with multiple copper fills. There's not much to fix there, as well as floating copper. Right now we have a lot of floating copper, but it's not possible to fix it. In the future, there will be a feature to get rid of them. But the one thing that you do definitely have to check are the air wires. And as you can see, we have air wires here. You can expand the drawer to click on which pad is not connected. So this way you can zoom out and trace the path to see if they're not connected. It's really helpful to click on these pads when you see air wires between ground paths. It's very common that you'll have some copper that's been clipped off and you have to add a stitching via to connect the ground paths together. So I just added this as an example, and I'm going to reconnect the trace. And as you can see, we have no air wires. I would do one last final scan looking at the copper, and in the next video, we'll be able to order our board.